Forget everything you thought you knew about alien life. We've always searched for exoplanets with oxygen, assuming it's essential for complex organisms. But what if we've been looking in the wrong place entirely? Prepare to have your mind blown as we explore worlds where life thrives in conditions that would suffocate us, and uncover the shocking biosignatures we'd need to find it. To understand the colossal shift happening in astrobiology, you first have to get why we were so fixated on finding a twin of our own world. The logic was simple, powerful, and deeply intuitive. It was based on the only data point we have: life on Earth. And here, two things seem inextricably linked to complex, active life: liquid water and free oxygen. This gave us the habitable zone, an idea that's dominated our search for decades. You've probably heard it called the Goldilocks zone. It's that orbital sweet spot around a star. Not too hot, not too cold, but just right for liquid water to exist on a planet's surface. Too close, and the oceans boil into a runaway greenhouse, like on Venus. Too far, and the world freezes, like Mars seems to be today. For decades, finding a rocky planet in this zone was the primary goal, the first filter in our cosmic sieve. But water was only half the story. The real prize, the silver bullet biosignature we were hunting for, was oxygen. In the vast and violent chemistry of the cosmos, free oxygen, O2, the molecule we breathe, is a profound anomaly. It's an incredibly reactive gas. Left on its own, it desperately wants to bind with other elements. It rusts iron. It oxidizes rocks. It reacts with volcanic gases. An atmosphere with lots of free oxygen is a system in a constant state of chemical emergency. Without something actively and continuously pumping it out, it would vanish in a geological blink. On Earth, that something is life, specifically photosynthesis. For billions of years, plants, algae, and cyanobacteria have been harnessing sunlight, splitting water, and releasing oxygen as a waste product. Our atmosphere, with its life-sustaining 21% oxygen, isn't a static feature. It's a biological construct, a planetary-scale life support system, built and maintained by life itself. The story of how Earth got this way is called the Great Oxygenation Event. For the first 2 billion years of life, our planet was an anaerobic world. Life thrived in murky, oxygen-free oceans. But then, about 2.4 billion years ago, cyanobacteria evolved a revolutionary trick: oxygenic photosynthesis. These tiny organisms began to flood the world with a toxic, highly reactive poison: oxygen. This was a planetary catastrophe. The new gas was lethal to most existing anaerobic life, causing the planet's first and perhaps greatest mass extinction. But from that disaster, a new possibility emerged. Oxygen created the ozone layer, shielding the surface from harmful UV radiation. More importantly, it offered a new, incredibly powerful way to generate energy. Life that could learn to not just survive oxygen, but to use it, would unlock an energetic jackpot. This paved the way for large, complex, active multicellular organisms, animals, us. This history became our roadmap for the stars. The assumption was baked into our models: if you want complex life, you need oxygen. A big oxygen atmosphere became the gold standard, the undeniable proof that a distant world was not just habitable, but inhabited. We built our most powerful telescopes, all to find that one specific spectral line of O2. It was a beautiful, compelling story, and for 70 years, it's the story we've been telling ourselves. The strategy was sound, and the logic was clear, but it led to a dead end. Decades of scanning the heavens for that familiar signature of oxygen have yielded an unnerving silence. This is the great mystery. We've found thousands of exoplanets. Over 6,000 have been confirmed to date by NASA, and many are in the habitable zone. But none have shown the clear, unambiguous sign of a living, breathing biosphere we were so sure we'd find. Then, as our tools got better, cracks began to appear in the foundation of our strategy. The James Webb Space Telescope, with its unprecedented power, started revealing a universe far more complex and deceptive than we had imagined. The first big problem came from the most common type of star in our galaxy, m-dwarfs. These are small, cool, red stars. Their habitable zones are snuggled up very close, which makes orbiting planets easier for us to find and study. But that closeness has a dangerous catch. M-dwarfs, especially when young, are violently active, blasting their planets with intense ultraviolet and X-ray radiation. Scientists realized this radiation could create a cruel cosmic illusion: oxygen on a completely lifeless world. The process is called photolysis. High-energy radiation strikes water vapor or carbon dioxide, splitting the molecules apart. The light hydrogen escapes to space, but the heavier oxygen gets left behind. Over millions of years, this can build up a substantial oxygen atmosphere on a world that is, and always has been, completely dead. Finding oxygen, our once unimpeachable silver bullet, was suddenly no longer a guarantee of life. It could be a trap, a false positive, fooling our most advanced telescopes. But an even more profound crack was forming in our Earth-centric model. It came from a revolutionary question: what is oxygen really for? For us, it's for breathing. But on a planetary scale, it's for burning. This insight led to the oxygen bottleneck concept, and it rewrites the rules for finding technological civilizations. The science is simple. To have open-air combustion, fire, you need a minimum concentration of oxygen. On Earth, studies show that threshold is about 16 to 18%. Our current atmosphere has 21% oxygen. Now, think about what that means for technology. Fire was humanity's first great leap. It let us cook food for more energy, stay warm, and, most critically, it's the gateway to metallurgy. Without fire, you can't smelt ore. Without ore, you don't get copper, bronze, or iron. Without metal, you don't build complex tools, engines, or electronics. There's no industrial revolution, no steam power, no electricity, no radio telescopes. A species could be brilliant, sentient, and philosophical. But without fire, they'd be forever trapped in a pre-industrial state, unable to build the very techno-signatures, like radio signals, that our SETI programs are designed to detect. This is the oxygen bottleneck. A planet might have life, even intelligent life, but if its atmospheric oxygen never gets above that critical 18% threshold, it can be a world of minds that will never develop advanced technology. It would be a biosphere, but it would never become a technosphere. Looking at Earth's history, we see this bottleneck. For most of our planet's past, even after the Great Oxygenation Event, oxygen levels were too low for sustained fire. It wasn't until about 420 million years ago that oxygen finally crossed that threshold and stabilized, opening the door for a technological species to eventually rise. Suddenly, the search for life fractured. If you're looking for ET, you now need worlds that not only have oxygen, but have a lot of it, likely over 18%. Those worlds might be incredibly rare. But what about all the others, the ones with life, but low or no oxygen? They wouldn't be silent because they were empty. They'd be silent because their inhabitants were not, and could never be, building radio telescopes. They would be home to silent biospheres. This is the revelation. This is where we throw away the mirror. Life isn't fundamentally about oxygen. It's about energy. All life is a machine for processing energy. It finds a source of chemical energy and uses it to grow, move, and reproduce. On Earth, the most successful strategy is aerobic respiration, using oxygen. But it's not the only way. To understand the difference, let's talk about life's universal energy currency, adenosine triphosphate, or ATP. Think of it as a tiny rechargeable battery for your cells. Every move you make, every thought you have, you're spending ATP. Here's the great energy divide. When one of your cells uses oxygen to break down a glucose molecule, it's a highly efficient process that yields a massive payout. Somewhere between 30 and 38 molecules of ATP. It's an incredibly powerful metabolic engine. Now, consider a life form that doesn't use oxygen, an anaerobe. It might break down that same glucose molecule using fermentation. The energy payout? A paltry 2 molecules of ATP. That's it. An aerobic organism gets roughly 15 times more energy from the same meal. This isn't a small difference. It's a fundamental chasm. It's the difference between a roaring blast furnace and a flickering candle. This energy gap forces us to imagine a slow-motion biology. On a world powered by anaerobic chemistry, life's pace would be glacial. With so little energy, metabolic rates would be incredibly slow. Imagine creatures whose every movement is deliberate, conserving every joule of energy. We might not see fast predators and prey, but vast, slow-moving grazers on the floor of a methane ocean, or colossal plant-like organisms whose life cycles span millennia. Evolution itself would be stretched out. On Earth, it took nearly 4 billion years, supercharged by oxygen, to produce us. On an anaerobic world, where the engine of evolution is running on a trickle of energy, that same process might take 20 billion years, 50 billion, or even longer. This isn't a problem for life around m-dwarf stars. They live for trillions of years, offering more than enough time for even the slowest evolution to achieve complexity. And let's be clear, this isn't just about microbial mats. Low energy doesn't rule out large, complex, multicellular life. Earth has pockets of complex anaerobic life that prove it's possible. Now, imagine a whole world where that's the only way. A world where evolution perfected the art of slow living. The creatures there might have senses we can't conceive of, and a biology that seems like magic, all powered by a slow-burning chemical fire that would be instantly extinguished by the oxygen we breathe. Because these worlds have no free oxygen, they are stuck behind the oxygen bottleneck. They are worlds without fire. This means they are fundamentally, permanently silent to our current search methods. They won't send radio signals. They won't light up cities. They won't pollute their atmospheres with industrial chemicals. They are silent biospheres, and the universe could be filled with them, teeming with complex life, while we've been completely blind, all because we were only looking for planets that looked and acted like ours. So, if we can't look for oxygen or listen for radio signals, how do we find these silent biospheres? We change the question. We stop asking, does this planet have the ingredients for life as we know it? And start asking, Is this planet doing something a dead world shouldn't? This is the search for a state of fundamental imbalance, or what scientists call thermodynamic disequilibrium. Imagine a dead, sterile planet. Over time, its chemistry settles into a state of balance or equilibrium. The gases in its atmosphere react until they reach their lowest energy state, a predictable, stable, and boring chemical landscape. Life is the enemy of equilibrium. Life actively works against chemical boredom. It takes in energy from a star, for instance, and uses it to create high-energy compounds, flooding its environment with waste gases that shouldn't exist together. It creates a planetary-scale chemical signature that screams, something is actively holding this system out of balance. This is the new biosignature. We're no longer looking for a single gas like oxygen. We're looking for an impossible chemical cocktail. The classic example on Earth is the coexistence of methane and oxygen. Methane is a flammable gas that reacts readily with oxygen, so it has a short lifespan in our atmosphere. Yet, we have a persistent trace of it. Why? Because living things are constantly pumping it out. The simultaneous presence of both is a powerful sign of a living planet. Now, apply this to an oxygen-free world. What would the signature be? Scientists believe the key combination could be methane, CH4, and carbon dioxide, CO2, in the presence of liquid water. On a dead, wet world, these gases aren't expected to coexist in large quantities. But on a living world, a global biosphere of methanogens could be constantly consuming CO2 and producing methane. Finding a planet with an atmosphere rich in both, plus evidence of an ocean, would be a monumental discovery, the fingerprint of a global anoxic metabolism. And this isn't just theory. The James Webb Space Telescope is already finding tantalizing hits. The poster child for this new frontier is K2-18b, a sub-Neptune world 124 light-years away. It orbits in its star's habitable zone, and JWST has confirmed the presence of both methane and carbon dioxide in its atmosphere. It also appears to be a high Ceon world candidate, a hypothetical planet with a deep-water ocean under a hydrogen-rich atmosphere. The key ingredients are there, but the most electrifying and controversial hint from K2-18b is the possible detection of dimethyl sulfide, or DMS. On Earth, DMS is almost exclusively produced by life, particularly marine phytoplankton. It's the compound responsible for the smell of the sea. The 2023 hints of DMS on K2-18b were tantalizing, but very weak. Many scientists have urged caution, pointing out how difficult it is to pull such a faint signal from the atmospheric noise. And subsequent analyses have shown that the evidence is far from a smoking gun. While the hint is exciting, it is not yet the definitive proof we're looking for. Still, the possibility is powerful. Scientists theorize that on a fully anaerobic world, a DMS-producing biosphere could be far more prolific than Earth's. With no oxygen to break it down, DMS could build up to concentrations thousands of times higher than here, making it a much easier signal for JWST to find. The hunt is on. K2-18b and worlds like it are the new frontier, and the evidence we seek is not the breath of life, but the chemical exhaust of a metabolism fundamentally alien to our own. This paradigm shift, from searching for Earth-like breaths to hunting for alien chemical imbalances, completely reframes our place in the cosmos and the Fermi paradox. Where is everybody? The paradox has always haunted us, but this new perspective offers a third, more hopeful answer. Maybe everybody is everywhere. Maybe the universe is teeming with life. But maybe the vast majority of that life is quiet. It is slow, deliberate, and metabolically constrained. It exists on worlds that never passed the oxygen bottleneck, and thus never developed fire, metallurgy, or radio. The Great Filter might not be a dramatic event, but the vast and persistent energy gap between anaerobic and aerobic life. It's a filter that doesn't stop intelligence, but it may prevent that intelligence from ever shouting across the void. This implies the most common form of complex life in the universe isn't like us. It might be the inhabitants of these silent biospheres. The Fermi paradox might just be a consequence of our own bias. We've been listening for shouts in a cosmos that overwhelmingly prefers to whisper. This new understanding will shape astrobiology for decades. The discoveries from JWST are just the start. The next generation of super telescopes, planned for the 2040s, will be designed not just to detect gases, but to measure their concentrations with incredible precision. They could directly test the oxygen bottleneck hypothesis by sorting worlds into potential technospheres with over 18% oxygen and silent biospheres with little to none. The search for ET could become far more targeted, while a whole new science opens up, the study of anoxic life. We'll hunt for the thermodynamic disequilibrium of methane, carbon dioxide, and other gases, searching for those unique chemical imbalances that signal a planet is not dead, but merely sleeping. We are at a pivotal moment. We are learning to shed our most deeply ingrained assumptions about what life is. The journey ahead will require patience and a radical sense of imagination. We are no longer just looking for another Earth. We are looking for something new, something strange, and something that will forever change our understanding of what it means to be alive. For a lifetime, our search for alien life was a search for a mirror. We looked to the stars for a reflection of ourselves, a blue planet, a breathable atmosphere. We listened for signals from beings we imagined would follow a path of fire and technology. But the reflection never came. Now, we're realizing our mistake was looking for a mirror in the first place. The universe may not be interested in reflecting us. It may be full of something far more wondrous, life that is truly, fundamentally alien. We're shifting our gaze from the single signature of oxygen to the subtle symphony of a planet's chemistry. We are learning to see life not as a set of ingredients, but as a process that drives a world away from the quiet equilibrium of death. We may soon discover that the cosmos is not empty. It's just quiet. It's filled with worlds that live their lives in a different key, at a different tempo. Worlds where evolution unfolds over eons. The question is no longer just, are we alone? The question is, are we ready to meet our truly alien neighbors? What other assumptions might we be getting wrong? If these slow-motion worlds exist, what kind of consciousness could arise? Let us know your wildest speculations in the comments below. Perhaps we aren't alone. Perhaps we've just been listening for shouts in a cosmos that prefers to whisper. If you enjoyed this journey, be sure to subscribe and hit the notification bell so you don't miss our next exploration into the biggest questions in the cosmos.